And hello everyone and hello professor. I am the Jihan. I will present about the explainable deepfake detection. Nice to meet you. And now these days we are living in the explosion of AI GC and blurred boundary of reality. In these days, the many kinds of the AI generative model like Sora and Fluix or the kind of Google Nano Banana, they can generate the very high quality images in these days. And you can see in these pictures, and I built it with the images when I take a photo and generate it with our university's characters. It's called Uni. And we can see that the image is very high quality, and you can check the very high quality pixels or kind of object in these images. So in now these days, we cannot be we cannot be check the real or fake the images. So I will prepare the simple quiz for you. And there is the two pictures in my slides. So can you guess what is the real image or fake image? If you think the left image the real image, can you raise your hand? Okay. And next, if you think a right image is the real image, please raise your hand. So the answer is the left image is the real image. And next quiz, there is a two image. So if you think the left image is the real image, please raise your hand. And this time is the right image is the real image. Please raise your hand. So real image was the left image. So in these days, we can this synthetic images or videos are now indistinguishable from reality at the pixel level. So there is the black box problem in the before models in kind of CNN or VIT models. So traditional SOTA models, they were focused on binary classification and from probability. So they couldn't say why the already classified the image was the real or fake for the reason. So we couldn't check the reason why they were classified the real or fake. So we can say there are problems about the black box problem. So we can check the three of the points. At the first time is the lack of interpretability. So cannot pinpoint specific artifacts like skin textures or mismatches lightly. And second is the trust gap. So difficult for humans to rely on 80% fake score in high stakes legal or social environments. And last is the debugging challenge. So cannot easily verify if a model is focusing on relevant artifacts or irrelevant noise. It's like kind of overfitting. So we meet the paradigm shift from the binary levels. So there is the new objective, so beyond the binary levels. So translating from is it fake to where and why is it fake. So our goal is bridging the gap between high dimensional features and human synthetics. So there is the VLM models to classify the real or fake images. So VLM can say we are combining eyes with the vision encoder with the brain, the LLM. So they can say the on the image input. So why is this image classified the fake image? Kind of. So some pixels were strange, or light things were strange in the image. The kind of things. So we can produce for the image classified reasoning. So at the first, there is a phase X-ray. This is the moving beyond the black box score. This is the first effort. So there is the problem. It's the traditional detectors. So only output the fake probability, like leaving users with no visual or local evidence. So phase X-ray has changed the game by shifting the focus from simple classification to visual localization. So it was the first major effort to provide visual evidence and based on the philosophy that a reliable detector should be able to point out the evidence of 4G. So phase X-ray's discovery is blending boundaries. In static image discrepancies like a noise or hardware or software marks exist across the boundary where two image meet. So you can check the boundaries in left or right image on the slides. And second is the base X-ray use the self-supervised learning. So they can be trained using only real images by creating artificial blended samples. And their output is the produced a grayscale image that reveals the location and shape of the blending boundary. So here's the phase X-rays contribution. So they can robust detection of unseen 4G types by assuming only the extenses of blending slide. So this slide can see the limitation of the phase X-ray. So first is the dependency on blending. They fail when an image is entirely syntactic, like fully generated again images, as no blending steps involved. And second is the lack of synthetic reasoning. So provides the where is anomaly, but cannot explain what or why in rational language. So you might see in that image on my slides. So we can check the location and shapes of boundary, but we can get the why or what is the problem. So last one is the interpretation gap. The grayscale map is still requires human expertise to interpret. It lacks the high-level cognitive logic of VLM. So second is the X squared DFT. So I will call the short name like a DFT. So this model's challenges is the MLLMs is often fail to capture a low-level artifact. So like kind of the frequency anomalies that are invisible to the naked eye. The effort is the moving from visual maps to linguistic reasoning by identifying what the models knows and what it misses. And key concept is the transitioning from a slide expert to an articulate decision maker that evaluate its own perception. So, and these models can maybe take an upgrade if the more better feature extractor or kind of some features, maybe. So you can upgrade the model's extractor, image extractor, or vision encoder. So it might be increase the performance. So the key features is hybrid intelligence, like an experts and plus LLM. So first things is the strong feature strengthening. So LLMs is often fail to capture low-level artifacts like frequency anomalies, so that are invisible to the naked eye. And second is the weak feature supplementing. This is the integrating external SOTA models like an MPR and FreeNet to fill the MLM's perceptual gaps. So this DFB paper's contribution is explainability. It provides detailed natural language reports based on multi-dimensional analysis. And second is extendability. So a flexible framework where new forensic tools can be easily integrated at plugins. And this slide is showed, you can see the DFD's performance and limits. So first time is quantitative excellence. So achieve SOTA results across multiple benchmarks. So you can check the right of these slides on the table. And significant improvements in both frames level and video level detection compared to conventional and vanilla MLM detectors. But there is the limitations too. The entire face synthetic is still underdeveloped compared to face swapping or attribute editing. So statistic focus is the current implementations is limited to static image detection. So this expansion to audio to visual effects. So this is the last paper in my presentation material. So it's called the fake VLM. The fake VLM can make the explanatory QA paradigm shift. So this paper's discovery is forcing the models to explain why an image is fake inherently improves its ability to identify it. So this model's key contributions is the first specialized large multimodal that achieves expert level performance without needing external black box classifiers. And they will make the fake load dataset too. So there's the zero branch architectures, over 100K images across the 7 categories, and animals and documents, and face manipulations and kind of things. And second is the multi-LLM LMM annotation pipelines. So they uses these 3 high-performance models like QWEN2VL or IncomeVL and Deepfake to generate candidate descriptions, and aggregation models ensures consistency and removes redundant information. And last one is the current failure cases, the high frequently images, the struggles with interceptable artifacts where syntactic inconsistencies are too subtitled. And last one is annotation bias. Is the reliability still depends on the base and LLM's useful library. And this is my last slide in my presentation. So their technology status is shifted from purely signal-based detection to human intelligence reasoning. And second is industry and real-world impact. The traditional probability score is insufficient for labor or social accountability. So fake Williams actionable evidence is from transparency and digital trust. So last one is remaining challenges. The expansion to video and audio visual deepfakes and mitigating the adversarial risk, the consistent race between generators and detectors. And thank you for listening.
Hello, my name is Sangmin Lee. Today's topic is egocentric vision and newly defined task and recent trend. Uh, Let me start by explaining the why egocentric vision is gaining so much attention. Uh, there are three main reasons. First, on the device side, wearable cameras such as Meta Aria, Quest 3, Apple Vision Pro are now commercially available. And second, on the dataset side, large-scale egocentric datasets have been released like Ego 40 and Ego X 40. And third, on the application side, practical use cases are expanding, including AR assistance and robot learning and healthcare monitoring. Uh, the slide shows the taxonomy of electronic egocentric vision based on a 2025 survey paper. It is divided into four main categories. Subject focus is on understanding the wearer themselves, uh, including gaze estimation and pose estimation and action recognition. Object focus is on understanding the object the wearer interact with, including object detection and identify, for instance, social interaction. And next, environment focuses on understanding the surrounding space, such as SLAM and localization. Finally, hybrid combines this element and include tasks like video, video summarization, and VQA. As you can see in the figure on the right, each category contains various subtasks. In today's presentation, I will focus on newly defined tasks that this survey couldn't fully cover. Uh, the first key challenge is egocentric vision is the limited data scale, while ego body is large data set, but exocentric data set like how to one 100 million contains over 134,000 hours of video. In other words, egocentric data is still orders of magnitude smaller. Uh, Two representative approach to address this are self-supervised pre-training and cross-view transfer. Next, the second challenge is the high dynamic nature of egocentric vision. Due to the characteristics of head-mounted camera, there is constant motion blur and frequent occlusion and out of view object and overexposure. The most significant distinction from exocentric. This is the most to address this. Multimodal fusion is being explored, which combines information from other modalities such as IMU and audio and gaze tracking with vision data. The third challenge is that a single egocentric vision contains information at multiple temporal scales. As you can see in the figure, within a single video, coarse granularity or text spans long time units covering the entire video, while fine granularity units such as action 1 and action 2 exist simultaneously at a shorter scale. Course level tasks require abstract summarize, and while fine level tasks require frame level decomposition. Approaches such as graph structure and hierarchical models are being used to handle this. The newly defined task, the first is episodic memory. The goal of episodic memory is to turn hours of egocentric video from AR glasses into a queryable memory store. This benchmark was defined in Ego 4D Challenge 2025 and consists of four subtasks. VQ2D is visual queries with 2D localization. It takes an object image as a query and find the last location where that object appeared in past video, returning a 2D bounding box. NLQ takes a natural language question as a query and return the corresponding temporal window. Next, moment queries finds all occurrence of a specific activity, something like show me every time I use the knife. Last goal step takes a step description from procedural activity and localize the corresponding temporal segment. Let me introduce Ego Body, the foundation dataset for episodic memory in more detail. Ego Body is large-scale egocentric dataset led by Meta, and an important aspect is that include narrations, the timestamp, natural language description of wearer's action. These narrations are not direct input to the task, but they are used as pre-training signals through a technique called NAQ. As shown in the table, Ego4D defines three episodic memory benchmark. VQ2D on takes an object image crop as a query and output the last seen frame with 2D bounding box. And NLQ takes a natural language question and outputs temporal window, starting time and ending time. MQ moment queries takes on activity name and outputs all matching temporal windows. Next is Ego4D goal step. This is extended benchmark added on the top of existing Ego4D. And while the original three tasks had a flat structure, finding individual actions, goal step deals with hierarchical procedural structure. The key is its three-level hierarchical annotation, goal and step and sub-step. Goal is top-level activity like make omelette, and step is intermediate level procedure like toast bread, and sub-step is fine-grained frame-level action like add oil or butter. OSGNet is champion solution that won first place in a three-track NLQ and MQ and goal step at the Ego4D episode memory challenge 2025. As shown this figure, OSGNet use two branches. The main branch fuses video features, text queries, and object features together. This is early fusion approach. This use early fusion approach, including object features is crucial because in egocentric video and object interaction are central. The sharp branch leverages Ego4D's rich narration data and applies contrastive learning between video shots and texture input. This strengthens cross-modal alignment. The second newly defined task is procedural error detection. Traditional anomaly detection on the left is binary detection at the level of something unusual happened, but procedural error detection on the right specifically identifies which step went wrong and how. The Ego4 dataset was presented CVPR 2024 and contains 28 hours of procedural activities annotated with 5 error type, omission and addition and sleep, modification, correction. Next. Prego is the first model to perform real-time mistake detection in egocentric procedural video. It has two key characteristics. First, it performs online detection, detecting errors in real time. Second, it uses one-class classification, training exclusive on normal procedural videos in order to detect unpredictable errors. The architecture is dual branch structure. The recognition branch recognizes the current action being performed in real time. The anticipation branch uses on llama-based LLM to predict the next expected action. through symbolic reasoning. If the actual action doesn't match the predicted action, it is flagged on error. T-Frego is an evolution of Frego, with the key upgrade being replaced, the replacement of the anticipation branch with Llama 3.1, and two prompt engineering techniques are applied in context learning and automatic chain of thought. The third task area is ego exo transfer and joint understanding. Ego view and exo view provide fundamentally different information like this figure, and ego exo body is large scale dataset released at CVPR 2024 containing more than 1,000 hours, and using Meta's area classes, it includes rich sensor data like this, and it also provides video language resource, expert commentary, third-person action descriptions, and first-person narrations. Here I show you the three types of video language resource. And, EgoXO body covers 8 categories of skilled human activities. Let me introduce three recent key studies. On the left, cross-view compilation model released CVPR 2024 by paper by Samsung Electronic and KAIST. It performs zero-shot correspond estimation, inferring occluded or unseen information across ego and exo viewpoint. In the center, Probe VLM is 2026 paper that analyzed multi-view video to evaluate human skill proficiency. It goes beyond simply recognizing action to assess proficiency levels and generate expert-level natural language feedback. And next, on the right, EXO to Ego Scene is a 2025 paper that uses diffusion-based generative model to synthesize ego video from EXO video. This can address the egocentric data security problem. The first task area is egocentric body and hand motion. The core problem of ego allo is that the wearer's body is invisible from head-mounted cameras. Since the camera is on the head, the body part itself is never captured. So the input is egocentric slam pose, and the output is fully body mesh through SMPLH parameters, including body pose and height and hand parameters. The motion uses conditional diffusion model by incorporating detected hand information from images as guidance, and it achieved 40% reduction in hand estimation error. Next is uni-ego motion. Previous method could only perform motion reconstruction. Uni-ego motion handles 3 tasks with one single model. First, reconstruction takes ego video and head trajectory as input and recovers past 3D fully body motions. Second, forecasting takes past ego video and trajectory and predict future motion. Given how I've been moving so far, this is how I'll move next. Uh, this is a novel task first defined in this paper. Third generation produces plausible full body motion from just a single ego image. This is also no task. The method uses a unified conditional diffusion model with head-centric motion representation. As shown in this figure, conditioning inputs are randomly masked during training, it allowing a single model to handle all three tasks. Here, I'll show you actual output of three tasks. And today, I introduced four newly defined tasks and in egocentric vision. Thank you.
Hello everyone, I'm Soe. Today I will be reviewing the paper SAM 3D Body, Robust Full Body Human Mesh Recovery, aka 3DB, recently released by Meta. To put it simply, the model proposed in this paper is comfortable 3D human mesh recovery. Moving beyond traditional passive estimation, it is the first model that allows users to control the inference process using prompts, like key points, boxes, or masks. This research doesn't just achieve top performance, it offers great insight through a paradigm shift in technical approaches, specifically in architecture design, parametric representation, and VLM-based data construction. To be specific, it ranks dominant number 1 in generalization for extreme poses and out-of-domain data, where previous model often failed. Existing HMR models are often overfitted to controlled lab environment. Because of this, they fail extremely when faced with extreme real-life poses, occlusion, or unusual camera angles. But the bigger issue is the integration paradox. There is a fundamental conflict between capturing the macro poses of the whole body and the micro detail of the fingers. They require completely different input resolution and camera estimation method. In previous framework, trying to optimize both at once caused them to crash, resulting in poor prediction for both. To solve this dilemma, this paper introduced 3 technical innovations. First, the author built 3DB on MHR instead of previous traditional SMPL, proposing a new parametric mesh representation that separates the skeleton and the shape. Second, they use an encoder-decoder architecture to effectively combine user prompts with image information. Third, there is two-way decoder that separates decoder for body and hands to resolve optimization conflict. However, even a powerful model has its limits without right data to back it up. To cover rare poses and extreme conditions, they built a VLM-based scalable data engine to self-produce high-quality training data. Now let's differ into these technical leaps from model architecture to data engine. First, the first core technology of 3DB is the promotable architecture. This is for architecture of 3DB. Traditional HMR models were passive. Example, you give them an image and they split out fixed results. However, 3DB works like SAM. It takes 2D key points or masks as prompts. Take a look at overall pipeline here. It uses a transformer-based encoder-decoder structure. The process of turning image, image and prompt into a 3D mesh happens in 3 steps. First, step 1, image and prompt encoder. The model extracts information. The image encoder compresses the person's form into a dense feature map app, while the prompt encoder converts users' hints like key points or mask into token the model can understand. And second, step two, decoder token. The model assembles 4 specific question queries to reconstruct the 3D body. First, where is the initial estimate? Two, where are the user's hint point? Third, where exactly are the hands? Fourth, what are the precise joint location and confidence level? Like this. These are combined into a single query set called T. Step 3, MHR decoder. Through cross-attention, the model compares the question T with the image data F to find the optimal body structure that reflects the user's intent. Finally, it calculates body and hand parameter independently and merges them into a sophisticated human mesh. The second innovation of 3DB is two-way decoder strategy. This was designed to solve the optimization conflict that happens when you try to calculate full body poses and finger movement at the same time. To stay efficient, 3DB shares a single image encoder. However, it splits the decoder into two branches, one for the body and one for the hand. The body decoder looks at the whole image to infer the overall pose. The hand decoder focuses specifically on the cropped feature map of hand area to capture the detail. Interestingly, the body decoder has built-in hand position token. It finds a hand using a bounding box first, calculates any uncertainty from occlusion, and then merge the hand decoder's result into final rendering. And third shift is how we represent the data itself. The biggest downside of the SMPL model is that the skeletal structure and the body shape are intertwined in the parameter space. 3DB breaks away from this by introducing MHR, Momentum Human Rig. The key to MHR is that it separates the skeleton from the shape. Because the MLP network can now regress the parameter, both shape, camera, and skeleton independently, the model can learn joint rotation and body size separately. This makes training more stable and drastically improve the interpretability of the 3D structure. Next is about data engine, which gives the model its robustness. Very key word. They use a VLM as a data curator. Instead of random sampling, they analyze where the current model was failing and gave a VLM-specific mining rule. For example, you had a VLM filter for high-value difficult samples, such as acrobatic poses and complex human-to-human interact or movement where hand and bodies overlapped. By repeating the cycle of evaluation and analysis and VLM search and retraining, they maximize data diversity and build a model that is incredibly robust in the wild environment. Finally, how do we get accurate 3D ground truth for this difficult image? We use a multi-stage pipeline for mesh fitting. While data diversity gives us robustness, this annotation process gives us accuracy. It follows a sophisticated flow, left down side, wrong side. First, a human correct the 2D key point from initial 3DB draft. And second, the algorithm then first fits optimizes the 3D mesh onto the image. And third, it creates high-quality 3D levels for training. In multi-view setup, the system uses triangulation, calculating where lines from difficult camera angle intersect in space to find the true 3D coordinates. By adding second-order optimization and temporal smoothness constraints, the model moved beyond just guessing, or like in single view, and generate 3D level based on solid geometric calculations, not just guessing. This is the secret behind 3D-based high accuracy. This is SOTA on OD. This part is 3DB. 네. Moving beyond just good performance, we need to focus on how robustly it model generalized. Existing model like HML 2.0 or WAM just suffer from dataset specific bias, where performance drops sharply when they encounter a new domain slightly different from their training data. In contrast, 3DB achieves an overwhelming total ranking even on 5 external datasets that it had never seen just during training. This proves that the VLM-based data engine isn't just about more data. It taught the model the essential edge cases needed to survive in the real world. Even as a full body model, its ability to match the precision of specialized hand model further proves 3D's structural flexibility. High metrics doesn't always guarantee high visual qualities. That's why we focus on the sweet spot, the precision that the human eye actually perceives. As you can see in extreme scenario in the below, extreme scenario where the body is cropped or upside down, other models often struggle with twisted parameters, creating automatically anatomically impossible shapes. However, thanks to MHR's skeleton shape decoupling, 3DB maintains structural integrity even in extreme poses. A large-scale preference survey of 7,800 people, 3DB recalled a dominant 83.8% win rate against its big competitors. This suggests that when we apply this model to the real-world environment like AR, VR, avatar, we can drastically reduce the uncanny valley effect for users. Ultimately, the key insight here is how we serve the trade-off between data quantity and quality. While HTML 2.0 competes with data amounts and one focuses on physical constancy, the 3DB chooses to use a VLM as a curator to pick the most efficient training samples and applies geometric accuracy to them. This strategic choice became the foundation for creating the most robust model at the lowest cost. While 3DB is powerful, I'll give some thought to remaining bottlenecks and future extension. The bottlenecks, first, lack of facial detail. Compared to sophisticated hand and feet, integrating facial expression remains a challenge, still a challenge. And second, prompt dependency. In automated pipeline, if the initial detector fails, the entire reconstruction can collapse. To overcome these bottlenecks problems, I propose two directions for future extension study. My thought, VLM driving closed loop system, we can move beyond manual annotation by creating a fully automated loop. Here, a VLM doesn't pick image. It compares the predicted 3D mesh with original image to self-correct error and auto-adjust prompt. And beyond mesh, integration with 3DGS. By combining 3D-based accurate 3D rig with 3D Gaussian splatting, we can beyond simple shapes. This would be allows us to create more realistic, real-time animated avatar. To wrap up, I'd like to suggest three horizons that 3DB offers for the future research. First, prompt integration. Using users' input as a cross-attention query is a powerful tool that can be applied immediately to segmentation or detection research. Second, VLM-based data engine. Instead of data sweating manual labor, we can maximize efficiency by letting AI find the model's weakness and select the data. Three, architectural decoupling. When learning object with different characteristics, the shared encoder and two-way decoder structure is a highly effective blueprint to consider. In conclusion, SAM 3D body isn't just about boosting performance by adding more parameters. It's a study that pushes the limits of 3D vision robustness through the synergy of structural separate MHR and interactivity, promptable, and intelligence data curation VLM engine. Thank you for listening. Is work for whole body and separate body and hand decoder, so accurately can predict hand and body both of them. No. Yes.
Hello, it's working. Right? Yeah, today I'm going to present about VLA in autonomous driving. So the first thing, this field has moved so quickly in the past 2 years or a year that we've changed it drastically. Before, as we know, there was a simple model where there is a perception, then there is planning and perception, detection, and planning. So in 2023, this was SOTA, the peak of autonomous driving. So it inputs 5 the images from the car camera, and it uses a normal model to transform it. So it detects the objects, and then it gives the coordinates. But in the recent 2 years, this changed, and there are some changes for the input, the output, and there is also new tasks. For the input, there is natural language. So before, if there was an object, so it detects and predicts where to go. Now they added natural language as a sensor. For example, you can input like if you want to turn to the left or to the right. So you get that as a text, and you also get the trajectories of the input data as a text as well. So this is a new kind of input, and the output. There is a new model called chain of thought reasoning. So before predicting where to go, they uh, they give you the reasoning, like why they choose this action. It's very similar to what the uh, natural language processing Gemini or what the typical AI does. So it's shifted from the black box, and it's gives a different data. And there's also new world modeling. They move from the passive object detection to active data synthesis. So when we want to generate new models, like for example, in a car crash, it's very difficult to get that data because it requires a lot of money and a lot of things. So right now, there are some papers that are building these kind of models. So here, I want to briefly mention the previously, the traditional modeler stack, and now they use unified VLA model. So the first paper I came across was from the Google and the Waymo. It's called EMMA, End-to-End Multimodal Model for Autonomous Driving. So in here, it uses 3 types of input. 2 of them is textual input, like natural language model. First one is from the router, like high-level command, for example, turn left or turn right. And the second is historical ego status, for example, what the car was going, how the car was going, the speed of the car, etc. And the next input is a visual input. It has 6 images from the 6 different position of the car, and they go to the model as a vision. And they are all fit into Gemini model. They build like Emma, which is built on top of the Gemini. So it uses all the complexities and all the reasoning capabilities of the Gemini. And at the output, it produces the future, the waypoints, as the waypoints show where should he go or where to do the action. Uh, Plus, it also gives 3 distinct things like spatial reasoning, why it chose this action, road comprehension, so it tries to understand what the road, the elements in the road, and the scene understanding. So Emma introduced chain of thought planning. They recast this driving as a visual, the questionnaire answering, like they give input as the vision and they answer it by text. So it can reason about the novel scenarios. For example, in the previous model, if there was a squirrel in the text, they can detect the squirrel, but they cannot do like the action. So in Emma, it avoids it without specific training data. Here, how the input prompts look, they first give the camera images and then navigation. Then there is a simple formula trained on top of the Gemini, which gives text and the vision, and it gives the output. There is an open research gap. Emma generates the reasoning trace, but there is no agreed metric to evaluate whether the chain of thought explanation is causally correct. So we don't know, like, it gives the output, but we don't know if the output is the correct way of doing that. So this is like they are currently working on. Here's a illustration of their generalist model. It's very similar to the previous slide. And here is how the visualization looks like. Here they detect a garbage bag on the freeway. So the trajectory is to slightly turn to the right and to avoid it. And it also works during the night as well. As you can see from the image, the construction zone blocks on the left. So the trajectory it suggests is passing through on the right. And it correctly estimates the results. Yes? Yeah, that was one of the limitations, like the latency the issues. But for this model, it's very similar to Gemini, the text output and the text. But the images, I'm not sure how they pass. But for the text one, they are very fast. And in all of this, they addressed it as a challenge. So I'm not sure if they solved it or not. The next model I want to discuss is AlphaMaya from NVIDIA. This is actually a very new paper. It's from 2026. It was presented in the conference with NVIDIA, and it's industry's first chain of thought VLA model for autonomous driving, and the architecture looks like this. So they introduce a new output technique, which is called chain of causation. Here they talk about the action, like what the action should be, and they put the reasoning. So first they answer the question why before where. So they generate the possible outcomes to why they should take that action, and then at the end they give the real result to where it should go. Here is casual reasoning trace. They link three observations. So, for example, vehicle ahead is braking hard, pedestrian stepping to the crosswalk, red road wet from recent rain. So the casual factor here is wet road increases stopping distance by 40%. So it uses that information, and the trajectory intersects the ego path in 2.1 seconds. It calculates it, and then it gives an output like high risk scenario. So the decision is hard to accelerate. So it reduced from 11.2 meter per second to 3 meter per second. So it yields the pedestrian and the prepare for emergency stop. So and it gets all of this information as the tokens, and it generates the token as well as the coordination of the input. Here's the architecture of the AlphaMaya R1. And see, maybe I can show the video if it is. I put the link here, but I think it's not updated one. So here is the outcomes. For example, the person in blue t-shirt is pushing a trolley. So that, it suggests that to be cautious because it might follow or interfere with the path. Also, if there is a construction worker, it says like to follow its instruction because it could be saying something important, and it works in the different scenarios too, and the weather conditions as well. And now from the previous two models were the action models, but this one is for generating a world model, which is for very rare situations like extreme weather or extreme like car accident situations. Here it takes all the dynamics. For example, you can change uh, the ego dynamics, the agent configuration, and they are all fit into the diffusion model that they trained. And output is 5 camera views of the car. So they generate what the world model should look like. Here is the generated version of Kai A2. It works across 3 countries, in Germany, UK, and the USA. The, the, the architecture looks like this, and they fit into a video tokenizer where they put the video and they get the pixel and the integer values, and they are all fit into one video tokenizer. Here's the generated results for extreme weather. And I want to talk about the capabilities of this model. It's very good for rare and safety critical scenario synthesis, like they stimulate or they make things that are very rare, and it could be very useful because it was one of the most difficult challenges for autonomous driving, because you don't know, like in difficult situations or in bad weather conditions, what actions should the car take. So by training with this model, it will learn how to do that. Also, it gives like multi-camera. It doesn't just give one camera, like the front camera, but it gives like the 5 cameras to see the better. And it has controllable what-if counterfacts, like you can actually change the weather or the agent, time of the day, and it will generate the condition according to your interest, and it works in 3 countries. Right now, beyond the camera and the LiDAR, they are making a new type of inputs, and there are always huge interest in these 4 specific fields. Like there are a lot of papers recently focusing on 4D imaging radar. They want to add first large-scale 4D radar dataset, and it was discussed in radar occlusion. And there is also the development in event cameras. They want to change it as well. And future directions, there is still unsolved problems in autonomous driving, and they want to solve it. For example, before there was the plan was like to track the trajectories independently, but now they want to answer the questions like, what if I want to go, can I drive through it or around it? So they want to answer critical VLA-based driving questions. And the one problem is off-road and non-urban perceptions. Like most of the data set, they are trained in the cities or non-urban places. So in the urban places, so it gives a large question in agriculture and the disaster zones on that different places. It still remains a question. Yeah, it's from the paper. Yeah. So like in the NVIDIA and the EMMA, they want to address this kind of problems. And here's my references. Thank you. World model. World model is just the model that they generate. Like for example, when you're driving a car, the world model is the three cameras, the front, in the front, and the two in the back. So in this, they generated the video sequence of the world model that could be used, like for example, in extreme weather. You cannot test, or it's very difficult to test what the car will do in that extreme conditions. So they generated a world model according to that extreme conditions. So I think it's very similar in terms of how they made it, but they called it generative world model in their paper. So I use this word. Yes. It mentioned that it's like how they did it is from the previous models, but they called it world model, and I think it's just for the field itself. Maybe I'm not sure.
So, anyways, this is all the contents we prepared for today.